So here is a problem, paper 1 for implicit differentiation. So, well, I think we can just understand paths as a curve. So like we have a curve with this equation, and with this restraint of domain and range. So we want to show that this curve has no local max or min of z as a function of x for x greater than 0. So we want to show that dz over dx can be 0 for this case. So let's first write this equation as the expanded form and move this 4x squared to the left side to help us differentiate more easily. So now we have this, and just apply implicit differentiation, and then isolate dz over dx, and then we get this fraction. So let's say if dz over dx equals 0, then that means the denominator should be equal to 0 to have a local max or minimum. So that means either x equals 0 or 4 minus d squared equals 0. It says that x is greater than 0, so only this can equal to 0. So let's see if that's possible. So if we look at the range for z, it's between -2 to 2, but not inclusive. So d squared can only be between 0 and 4, and it can equal to 0 but not 4, because d cannot equal to -2 or 2. So actually, d squared is positive and it's smaller than 4, so 4 minus d squared must be greater than 0. That means this whole thing is greater than 0 and thus not equaling to 0, so the derivative cannot be 0 in this case, and thus no local max or minimum. This question involves some trig calculations, like basic ones, and some implicit differentiation. So we have a curve that looks like this, and y cannot be 0. So first we want to differentiate implicitly to show that the derivative equals this. Well, for this one, you don't have to move this to the right side or this to the left side. You can just do it directly, like differentiate directly. So remember to write dy over dx for the terms that has y, and also for this we need to apply a product rule. So after isolating dy over dx, you'll get this, and that exactly looks like what's in the question. Now we want to show that if dy over dx equals 0 at this point on d, then y equals to plus or minus 1. So let's set dy over dx to 0. So that means the numerator equals 0. Well, y cannot be 0, it's stated, so it can only be cosine xy equals to 0. Well, if cosine something equals to 0, then sine of something must be equal to plus or minus 1. Well, if we look back at the unit circle, like cosine is on the x-axis, so it can only be this point or this point. So sine xy can only be 1 or -1 when cosine xy is 0. So that's how it looks like. And sine xy is actually in the original formula. So if that thing equals 1, then y to the power of 2 equals 1. So if y to the power of 2 equals 1, then y can be plus or minus 1. And now we want to find the coordinates of all points on D for x in this domain where the derivative equals 0. So just as what we wrote before, if the derivative is 0, then it's cosine xy that equals 0. So there are two cases, like because y can equal to plus or minus 1. So we can write cosine x, which is cosine times 1, equals to 0, or cosine x times negative 1 equals to 0. So that's the two cases for the two possibilities of y. And we want to see what are the x values we can get that equals to, makes cosine x or cosine negative x equal to 0 within this domain. So for the first one, like, you can think about it using the unit circle, like when does cosine of something equal to 0? So you can go from here to here, that's like 90 degrees pi over 2. You can go from here to here, that's 270 degrees, that's 3 pi over 2. And you can go back again to here, and that makes it 5 pi over 2, and then at last you have 7 pi over 2 without exceeding 4 pi. So that's the four x values here. And if we want cosine of negative x to equal to 0, well then we can only go from this side. But that will cause it to be negative. Like x will become negative. However, here we have x only as positive. So like we have no new solutions for this case. Well, we have these four x values as our solutions. So what we can do is that, well, find that at each x value, whether y equals 1 or negative 1. So y to the power of 2 is still 1. And then we can just write on the other side is sine of, well, we can do like x1 times y, that equals to 1, and then solve for y. So after you solve for each of them, you write out the four coordinates, and then you get the question done. You have to write these because it's asking you the coordinates, not just the x values or just the y values. This question is quite comprehensive. It contains implicit differentiation in part 1, and then related rates in part 2, and in part 3, it tests you on the knowledge for vertical tangent. So like vertical tangent is when the tangent is like basically like a vertical line. And after we differentiate it, we can analyze like how to make it a vertical line, like what happens to the denominator to make it look like that. So let's first do implicit differentiation on this equation. Just remember that like ln x, like the derivative is 1 over x, yeah. And apply product rule here. So after isolating dy over dx, you will get this, which looks exactly like what's in the answer and also in the question. Just very important, like when you also do the step, and when you get here, like here are two negative signs, right? And in the question, like it pulls out the big negative sign down here, and here it becomes positive. So it's actually like negative and negative to positive, and that's also negative, so negative, negative. But like it's like they write it this way. So imagine there's like a bracket here. So do not get confused when you have a negative sign and a negative sign here, while there's negative and positive, because they're fundamentally meaning different things. But like still the answer is the same. Just make sure you write it that way. So now the x coordinate increases at a rate of dx over dt given as half, and then dy dt, we need to find that when x equals 0.7, and we can use a calculator for this. So remember the golden formula, like dy dt is the rate of interest and dx over dt is given, right? And what is missing to build this equation is dy over dx, right? And that's what we did in part 1. So we substitute 0.5 here, and then we find the numerical value of this when x equals 0.7. And then we can find dy over dt. So that is what I wrote before, and then we just write dx over dt as 0.5 and dy over dt as this. Well, notice that not only it has x in there, which is 0.7, it also has y, but we don't know y yet. So like we need to find y. And we gotta use this original equation to do that. So use your calculator to find y, and it's like about 0.038. Then you substitute x and y in this part, and then the final answer for dy over dt should be rounded to 2.90. And now we want the coordinates when the curve has a vertical tangent. So the derivative is written in a fraction form. Remember, a horizontal tangent is when dy over dx equals 0, right? That's because the top equals 0, like the numerator equals 0. But for a vertical tangent, it's actually the denominator that equals to 0, because it's like you divide a number, like just imagine it as you divide a number by 0 and it becomes infinity. Like, because if you divide it by a really small positive number, then it becomes like a really large positive number. Well, if this thing is positive, right? So like if you divide it by 0, just imagine it goes to infinity. So, and when it's infinity, like it's infinitely slow, like steep, right? So when it's vertical, it's like the steepest, which is the denominator equals 0. So that means x ln x equals to 0. But we know that x is greater than 0. So it can only be ln x that equals to 0. So when ln x equals to 0, we know that x equals to 1, because like log 1, ln 1, they always equal to 0. So let's find the coordinates, because it's asking us like x comma y. So sub x equals to 1 in there, and then try to find y. But you'll see that like you can't really find y. Like y just disappears, because like you have ln 1 right here after substitution, that becomes 0, and then you end up with e plus 0 equals 2, and e should not be equal to 2, right? So that means this point we want doesn't exist. So like there are actually no points with a vertical tangent. The question maybe it doesn't look like that, or doesn't imply that it doesn't have a coordinate, because it seems to ask you to find it. But if you do find that, oh, it's impossible to have that coordinate, then just please write it. Trust your math skills for that. So this is an interesting problem about related rates. So we have a lunar satellite moving along a curve shown by this formula, where x equals xt and y equals yt in thousands of kilometers and t in seconds. So you will notice that this is the circular graph formula. So yeah, because we have a satellite, so the graph actually looks like this. Like the satellite is moving around like this, and that's x and that's y-axis. So when you're calculating, like, it is okay to get like a negative x value or negative y value, although they're like distances, because like we are just setting the coordinates like this and it's moving in a circular way. So that's just an observation. And given that dx over dt is this 1000 km per second and x equals this at this moment, and we want to find the possible values, so there are more answers probably, of dy over dt in 1000 kilometers per second, and our answer should be in standard form. So that means scientific notation. Okay, so it's like something point something 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 times 10 to the power of like a whole number. It's like between 1 and 9, like essentially like that number. Yeah. So we are gonna use that golden formula again for related rates. We always use it. So dy over dt is what we are interested in, and so it equals to dy over dx times dx over dt. Same reason, cancel, and you have the same thing. We are already given dx over dt, so we need to find this from this formula. So let's just implicitly differentiate it and then isolate dy over dx, and then we get this. So we have this and this together multiplied, which equals to dy over dt. However, we have y value in here, so just like another previous question, we gotta find y first and then substitute it in here and substitute x in here to get a numerical value. So how do we find y? We can find y using this original equation, like the original formula. So substitute x in there and you have y squared right here, right? So it actually naturally yields to two possible solutions for y because it's a degree of 2. So by GDC, you have y1 equals to 0.118 thousand of kilometers and y2 equals to negative 0.118 thousands of kilometers. And here is just what my GDC shows. So like the y line is like y equals 1, and when y equals 1, there are these two possible y values intersecting with it. So now we get all the numbers we need. So let's just find the two possible rates for y. So using y1, we can have dy over dt equals to, this is dx over dt times what we substitute here for dy over dx. So y1 is 0.118. We substitute 0.118 down here and substitute x here. So we eventually get this, right, in thousands of kilometers per second. And for y2, it's the same method, but we just use another y. And then we get essentially a positive value here in the same unit. So that's how it works. And yes, this is in scientific notations. So what I mean by from between 1 and 9 is that this number should be between 1 and 9, like -1 and -9. And this should be like integer power for 10. So this is another paper 2 related rates question. It's similar to what we did before. It's a conical tank and it's inverted. Well, I think for these type of questions, there are basically always inverted. With a max height of 12 meters and radius of 4 meters, being filled with water at a rate of 2. So like the water fills from the bottom and goes up, right? So the height and the radius increases. So we want to find the rate at the height is increasing, like dH over dt, when h equals 6. So golden formula, right? dH over dt will be used. And what's also something we use very often, right? We have height, we have radius, so we can have volume, right? So dV over dt should also be used. And actually we're given dV over dt, which is just 2, right? It's filling in this rate. So we can bridge them. Well, how do we bridge them? Sorry. So we can make dV over dt equal to dV over dH times dH over dt, because we're getting rid of dH, so it has to be like in the numerator and denominator of two separate fractions, right? So we already know this, and we want to know this, and we can find something for this. So the volume formula for a cone is this, and we don't want to have two variables in there, so let's find a relationship between h and r, right? So h equals 3r, and r equals h over 3. So we want to substitute r, and by doing so, we will have v equals this. And let's just differentiate this, dv over dh, and that will yield to this. And then when we substitute h equals 6, we will have 4 pi. So let's substitute this numerical value and this numerical value to find dh over dt. So 2 equals to 4 pi dh over dt. So dh over dt equals to 1 over 2 pi, and using your calculator, it's just 0.159 meters per minute. So this one is like a really quick implicit differentiation, and it's also for a conical tank inverted. So we're just implicitly differentiating this with dr over dh. Oh, this time you don't need to move 16 to the left side, because that derivative of this will just be 0. So just apply product rule here, and also dr over dh should be multiplied in here, and just ensure you have what you need and isolate dr over dh, and that's what you will have. Here is a mathematical induction problem on, I would say, differentiation. Yeah, basically. It's quite important. Like, it takes up 7 marks, and it's paper 1. And it might look confusing at first, so I want to cover it because I think it's quite important to get comfortable with calculus inductions. Let's read it. So here, z, we have z and we have z, right? So this is a function of z, and we're differentiating that. And n is like if n equals 1, like it's just the first derivative. If n equals 2, and that's the second derivative. So we want to prove that this always looks like this, and n is like z plus, so it's like 1, 2, 3, 4, 5, 6. So that's corresponding to what I said about first derivative to the nth derivative, right? P is a rational number, z is a real number. Alright, so like there are a lot of letters here, But our letter of interest, like the one that really matters in the proof, is n. And the variable that matters is z. So n and z are important. N is for the nth derivative, and z, well, that's just like the variable in this function thing. Yeah. So we're gonna write like a statement as always. Let Pn be this thing, copy it down, and for n as z plus, and p is a rational number and z is a real number. So we have a statement to look like this. Remember in proof by induction, we always test the base case. The base case for this is the smallest n, so that equals 1. So n equals 1, okay? So let's test the first derivative. We write it like this. So we're just differentiating this as a function of z, and let's do it. So here we need product rule, okay? So we have e to the power of pz because, well, the derivative of z is just 1, plus z times this thing differentiated, which is e to the p z power times the extra p. Well, remember, p is a number, okay? Z is the variable of interest. So we gotta multiply by z here due to chain rule. And, well, we can pull out e to the power of pz. So we have this factored out like this, and then we can make it look like this form, right? So how? So we already have this, and we already have this, right? N equals 1 here. So we need this. How do we get it? Well, p to the power of 1 minus 1 equals to p to the power of 0, and that equals 1. So essentially, we can write this derivative exactly like this, which satisfies the right-hand side. So since the left-hand side equals the right-hand side, P1, the base case, is true. Now we need to make an assumption for pk. So let's assume pk is true, for k is a positive integer, and we write this means this thing is true. So this is just all the letter n replaced by letter k, okay? And in the third step, we want to show that pk plus 1 must be true if pk is true. So like the domino falls, right? The domino falls. That's the rule of induction. So that means this thing is true. What we do is that we just replace k with k plus 1. So I prefer starting on the left-hand side because we are differentiating something. So it's better to start with like the original function and differentiate it to make it look like a final answer, right? So there's another way we can write the k plus 1's derivative of z times e to the power of pz, right? So remember that this is the case derivative, and it looks like this. So we can write that the first derivative of this, which is written like that, is actually the same as this. The original thing taken to the k plus 1's derivative is the original thing taken to the case derivative and taken derivative once more, right? So they are the same thing. But we need to write it in a new form like this to help us derive it much easier, because there's no way we're going to derive to the k plus 1's derivative, right? So now what I do is that I just expand it because it will facilitate differentiation. And now let's just differentiate it. Remember, like, the variable of interest is only z, right? it's only here in 3 places. So we can pull out p to the power of k minus 1 directly and differentiate what's inside. So here we have product rule. So it's p and bracket and the derivative of this thing, which is actually really similar to what we did previously. Right here. It's the same thing. So you just do the product rule derivative plus the derivative of this thing, and remember chain rule right here, so we gotta multiply by p. So now we're basically done. You see we have p here and we have p here, so we can actually factor out p entirely from here inside this middle bracket, and then we have this thing. So notice that you can arrange things together to make this product look like this. We are approaching it, right? How do we approach it? So we have p to the power of k minus 1, and then we have p inside. So why not let's multiply this and this. So now we have p, right? It's like this p to the power of k minus 1 plus 1, which is equal to p, right? To the k, sorry. Yeah, so we have p to the power of k already. So we achieve this. And now we want to achieve whatever that looks like this. And notice that we can factor out e to the power of pz, right? So let's do that. And look, we have exactly achieved what the right-hand side should look like. So the left-hand side equals the right-hand side. Like, the whole logic of this is to make the left-hand side look like something that is equivalent to it, but looks different. And how do we do it? We refer to the step 2. We refer to something in step 2. We substitute something with step 2 into here to modify what the left-hand side looks like. And now we have like a new form, and we want to manipulate this new form algebraically, manipulate it, look at it step by step, and then see how we can manipulate it to make it eventually look like this. So that's like the logic behind induction. Step by step showing. So it's like a big show question, right? Showing that the left-hand side becomes the right-hand side after substitution and algebraic manipulation. So don't forget the concluding sentence. Let's read it. Since we have verified the base case and shown that if pk is true, then pk plus 1 must be true. By the principles of mathematical induction, Pn is true for n is a positive integer. And that's it. We have covered 21 past paper IB questions in HL, and yeah, thanks for watching and good luck on your test.